Hi everyone. So in this video, I'm just going to find the matrix of the transformation relative to bases for about 4 or 5 different transformations, just so that you're completely sure you know how to compute it. It's not really difficult to do. So let's go try a couple times. Let's suppose you have a linear transformation going from P1 to P2. The transformation will take the polynomial first degree and just multiply it by x. Of course, then you'll get a polynomial of at most degree 2. The basis used will be the standard basis for P1 and the standard basis for P2. That's B and C. I want to find the matrix of M relative to B and C. So this would be the matrix of the transformation from B to C. To do so, just apply the transformation to every vector in B. So M of 1 is x, M of x is then x times x, that's x squared. Next, I have to go find out what are those images relative to C. So then C is 1x, x squared. So I have to write all those images as linear combinations of 1x and x squared. So I did that for M1, I did it for MX. And that allows me then to write down what those vectors, what those images are relative to C. So the images then are 0, 1, 0 and 0, 0, 1. Those are the two columns in the matrix. So the matrix of M from B to C is then equal to the matrix 0, 0, 1, 0, 0, 1. Now, if you understood what I did, let's just go test it. Remember, there's 2 ways to get to the same representation. So we have the vector 2x. I'll apply M to it to get 2x plus x squared. I'll then find the coordinates of that relative to C. That's 0, 2, 1. So remember, that is a representation of the image. Cool. And that's a representation of that vector, that polynomial in P2. All right, so start and go the other way. Let's say I have the vector again. This time, let's find the coordinates of it relative to B. Remember, the basis is 1x. So then those coordinates are then 2, 1. Then I'll take those coordinates and multiply it on the left by the standard matrix of M. Well, sorry, not the standard matrix, the matrix of M from B to C. If you look at the notation, it's very, very suggestive about what we're trying to get in the end. So then this takes B and it converts it into C. So this has to be something relative to C. And it's the image of B, of M, of V, relative to C. So you can see you get the exact same answer. Again, notice, again, remember, this is not the vector. This is just a representation of that vector. These are the coordinates. If you want the vector, you have to write the corresponding linear combination using those coordinates for the basis C. So MV is still the same vector. It's 2x plus x squared. All right, let's do it again. So this time, let's have a linear transformation E that goes from P2 to R2. The linear transformation will be E of Px will be a vector whose first coordinate is evaluating the polynomial 1, and the second coordinate will be the polynomial evaluated 2. We'll say that B and C are the basis for P2 and R2. B is just the standard basis for P2, but C won't be. We'll make a little difference. C then is the vectors 0, 1 and 1, 1. We know that is a basis for R2. I want to find the matrix of E relative to B and C. So this matrix of E from B to C. To do so, I have to take E and apply it to every vector in the basis of B. So there you go. I just smashed it out. Remember, E of 1, 1's a function. So if you evaluate the function 1 at 1, you get 1. You evaluate the function 1 at 2, you get 1. If you evaluate the function x at 1, you get 1. If you evaluate the function x at 2, you get 2. If you evaluate the function x squared at 1, you get 1. You evaluate the function x squared at 2, you get 4. That explains the vectors. Now I have to find the coordinates. So then I have to take those images and I have to find the coordinates relative to C. So the basis C was 0, 1, 1, 1. So each of the images, I'll write them as linear combinations of those vectors. So you get that linear combination for this one, that linear combination for that one, that linear combination for that one. So then I can find the coordinates of the images relative to C. Those are the coordinates. Cool. Now that I have that, I then know the matrix. Oh, the matrix of E, not M. E, not M. So that's a mistake. That should be E. E. The matrix of E from B to C is just the matrix 0, 1, 3, 1, 1, 1. Notice that the matrix is 2 by 3. It's 2 because there were 2 vectors in C, and it's 3 because there's 3 vectors in B. All right, once again, let's just test it. So here's the mappings, and let's take the vector in P2, 1, x squared. Let's apply E to it, and then see what the coordinates are relative to C. And then we'll come back, we'll find the coordinates relative to B, then we'll multiply it by the matrix of E relative to B to C, and we should get the same coordinates. So E of V is found by just taking the function 1 plus x squared, evaluating it at 1, evaluating it at 2. Those are the vectors. So that's 2, 5. Notice that that is 3 times 0, 1 plus 2 times 1, 1. So I did it again. So then the coordinates of EV, coordinates of EV relative to C is the scalars used in that linear combination, 3, 2. Cool. This time, let's go back and let's find the coordinates relative to B first. Then I'll multiply this thing 2 on the left, the matrix of B relative to the basis B to C. And that would be this product, which is notice the same coordinates. So you can get the same coordinates of the image either way. Either way. Great. Let's do it again. So then this time, let's define a vector space. Ooh. Define a vector space, which is the span of these 3 functions. So we know it's a vector space because the span is a vector space. It's a subspace of the set of all functions. So it's certainly a vector space by itself. And you should notice that if you take the derivative operator, take the derivative of any linear combination of those 3 functions, you'll get a linear combination of those 3 functions. So the linear transformation would then be applied to the space, will send you right back to that space. So then D will be the linear transformation from S to S, and all it is just the derivative operator. We'll use the basis being the very vectors that form the span. I want to find the matrix of D relative to B. Notice there's only one basis this time, because there's only one space, and I only want one basis. Well, to do so, I have to start off by applying the operator to each of the elements in the basis. So then I need to know what is D of E to the 2x. I need to know what is D of x times E to the 2x. I need to know what D of x squared E to the 2x is. Next, I have to go back and find out all those images. I need to know the coordinates relative to B. So then here's those products, if you remember. Notice they're already linear combinations of the 2 vectors I'm interested in. So then the coordinates are given this way. From here, now that I have the coordinates, they make up the columns of the matrix of D relative to B. So the matrix of D relative to B is just the matrix 2, 1, 0, 1, 2, 2, 0, 0, 2. If I'm right, we should be able to take a single vector and map it over to get the image of the transformation's coordinates 2 different ways. So let's go do that. Here is the transformation again, just to remind you, and here is the matrix of D relative to B. I just gave you a random vector V. I'll apply D to it, which means take the derivative of that thing. Oh God, so I smashed out the derivative for you. And then I can write down the coordinates of that image relative to B. Relative to B, there shouldn't be a C there. Relative to B. Relative to B. I'll do it again. So then I start with the vector. This time I'll find its coordinates relative to B. There it is. And then I'll just multiply this coordinate vector on the left by the matrix of the transformation D relative to B. And when I do so, notice you get the same thing. So you can get the representation of the image relative to B 2 different ways, whatever's convenient for you at the time. Great. Let's do it again. After this, though, we're done. So look at the identity linear transformation going from V to V. And we'll have 2 bases, the basis V, the basis B, which has V1, V2, V up to Vn, and the basis C. Obviously, since B and C are bases for V, the same vector space, and we already have a finite vector space, a finite dimension for V because the number of vectors in B is n, then the number of vectors in C has to also be n. Has to also be n. I want to find the matrix of this identity linear transform with respect to B to C. So to do so, to find the matrix of I relative to B and C, I have to take I and apply it to every vector in the basis. I then have to find its coordinates relative to C. But when you take I of a vector, it's just the vector because that's the identity mapping. So you just get the vector. That gives you that. But hopefully you recognize that that's actually the matrix that corresponds to the change of basis matrix. That is actually the change of basis matrix going from B to C. Neat. So the identity linear transformation relative to the basis B to C, when you write down the matrix corresponding to it, it's just the change of basis matrix. It's really cool. We can have to do further. If you want to know what is the standard matrix for I just relative to C, so that's C to C. Well, then that's the matrix of I relative to going from C to C. Well, that's the change of basis matrix going from C to C. The change of basis matrix from C to C means it's the matrix. Now, if you give me the vector's coordinates in C, I'm going to give you right back the coordinates relative to C. Well, that has to be the original vector. So the only mapping that does that is the identity matrix. So the identity transformation relative to only one basis is actually just the identity matrix. And I believe this is enough examples. We can then use these examples in later videos.